Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we're going to be talking about a good application of derivatives and how they kind of give us max and min values of a function. So firstly, I'd like to start off with a distinction between some of the terminology that we're going to be using within this lesson. So I'm going to start off with a couple of terms here. This one is a local, and we can also say global or absolute. So these two terms right here are interchangeable. However, most people say absolute. However, I have heard global being used before. We'll go over the definition, but graphically what a local min and versus a global like min or max would look like is something like this. I'm going to draw a graph real quick and I will illustrate to you the difference, but we will go over it. So let's pretend that we have this function right here, and we're going to make it continuous, but I'm not going to put the arrows at the end of it. But let's pretend that we have this function, right? As we can see, the tallest point in this function right here is up here, and the lowest point is over here. Actually, let's say that this function does terminate right here, just for simplicity. So we'll say that this point right here is higher than this one, even though it might not look like it, but let's just say that this one is going to be higher. So this right here, this point, is something that we'd call a global or absolute max, meaning it is the absolute max of the function. There is no more value greater than this one. And likewise, we would call this the absolute minimum or the global minimum, because it is the smallest value that this function contains. However, we can also have like intermediate maxes or mins, as we see along here, right? This is a local minimum. It's local to like areas that are near that value. Likewise with this this local max, it's local only to like areas around it. So that's kind of just a visual distinction between these two terminologies right here, or whatever you want to call them. But local is local to that area versus global or absolute. It just basically means that it is like the one and only max or min of the function. So here's the definition for absolute, maximum, and minimum values. We'll start off by letting this constant c be a number in the domain, which we called here d, of this arbitrary function f, right? Then we say that the function at this value c is the absolute maximum of f on this interval of d, which is the entire domain, if f of c is greater than f of x, and then this upside down a means for all x belonging to d, meaning for every x value that we come across in its domain, f of c is greater than any value, any x value that f is evaluated at. Kind of like what we saw right here, right? This value right here, the x value, this x value is greater than every single y value that this function can be evaluated at, right? So if we call this c, f of c is greater than all the x's that this function can be evaluated at. Likewise, for the absolute minimum value of f on this interval d, which is again the domain, if f of c is less than every value of x belonging to this domain of d, right, that means that it is the smallest value, like we see right here, because let's say now this is c right here, f of c is less than f of x for every single x that we can find. Like we take any x along here, the value evaluated at the x value will be greater than f of c. So therefore we call f of c the absolute minimum value of f. So likewise, we have the definition for local maximum and minimum values, and we basically establish the same c value and then the same domain. However, we say that a number like f of c is a local maximum of f if f of c is greater than f of x when x is near c. So like we see, the definition varies because we're no longer talking about the entire domain of the function. We're talking about just when x is near this value of c. And likewise for the local minimum value of f, if f of x is greater than f of c when x is near c, then it becomes a local minimum. So we could see that the absolute ones, absolute, local, min, and maxes, deal with the entire domain of the function. However, local minimum and maximums will deal with only like a small subset of the domain. So maybe just this portion, or maybe just this portion right here. So these bring us to the extreme value theorem. And the theorem is like pretty intuitive. I'll show you graphically why it like makes sense. But the theorem goes like this: if f is continuous on an interval, this closed interval actually, a to b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f at d, at some numbers c and d that are in this interval. So here I've drawn a couple sketches kind of illustrating what this extreme value theorem is about. And let's just choose these red markers to be our endpoints a and b. And we can see that if we draw it up to the function, we can see that every function is bound to have an absolute maximum or an absolute minimum on this interval right here, right? For example, this function, its minimum is going to be down here. However, its maximum might be somewhere up here. And this is true for all functions, like this theorem says. That's all this theorem is about, that if we have this interval, that there is bound to be an absolute maximum and an absolute minimum on that interval. So here, for example, we can have either one of these as our minimums, and then we can have a value like up here that is our maximum. Likewise for this last function, right? Our minimum is down here, and then our maximum would be somewhere up there. So you could see why it's pretty intuitive that every function is bound to have a maximum or a minimum value on some interval. So this brings us to Fermat's theorem, and he made this theorem that basically says if we have a local max or a min at this value c, then the other condition is that f prime at c exists, obviously, then f prime at c is equal to 0. And basically what this means is that the local absolute at this point, local or absolute maxes or mins have a derivative at that value of 0. Now, to illustrate graphically why this makes sense, let's pretend that we have this function, and again, it'll be on this interval right here, right? So here's a minimum, here's a minimum, but let's examine the maximum of this function, right? We could see that we know that the derivative, firstly, is the rate of change, right? Or it's the like the slope. So if we draw a tangent here, right, then we have a tangent here, and then once we move closer and closer to our max, we could see that eventually the tangent becomes a horizontal line. And what we know about horizontal lines is that the slope of a horizontal line is undefined. Likewise, if we were to have a function, I'm just going to freehand this one real quick, but if we were to have the like opposite function where we would have a minimum, again, our slope would slowly come to this horizontal line, and again, the slope here would be 0. So this brings us to critical numbers or values. They're used interchangeably, but essentially a critical value of a function is a number in the domain of f, and it follows this condition that the derivative of that value is either 0 or it does not exist. This DNE is just short form for does not exist. So this means one of two things: either it is a horizontal line, meaning it's going to have a slope of 0, or it's a vertical tangent line, because we know that the slope of a vertical line is undefined. So we know that critical values will have a derivative of 0, or it does not exist at that value. And we know graphically this would mean that there is a horizontal tangent line there or a vertical tangent line. So all of this brings us back to why we are doing this stuff, right? We want to find maximum and minimum values because they're going to help us see how this function kind of behaves. Well, we're going to be able to sketch the function a lot better. And this brings us to our last talking point, which is the closed interval method. And essentially what this is it's helpful to find an absolute max or min on a continuous interval. It's basically 3 steps. They're very, very simple, but if you follow them, you're guaranteed to find a absolute maximum or minimum on that interval. So I'm going to list the steps, then we're going to go through an example and apply them. So here are the 3 steps. First, we're going to find the critical values of f on this open interval from a to b, right? And we can do this by using what we've learned about critical values. It means that the derivative is equal to 0. And we'll see how we can do that in the example coming up. But that's all we're going to do. We're just going to find where the derivative equals 0 or it does not exist. Secondly, we want to test these endpoints. Because we found these critical values on this right here, this open interval, we also want to test the endpoints of this interval, right? And lastly, we just want to compare the values that we've got between these 2 steps from step 1 and step 2 to decide which ones are the absolute maxes and mins. So like I said, here is an example, and it tells us to find the absolute max and min of this function right here on this closed interval. So we're going to use the closed interval method and follow the 3 steps, and then we'll see how that leads us to the solution. So step number 1. Step number 1 of the closed interval method told us to find the critical values of f on this open interval a to b. So let's do that. We can basically do that by setting the derivative of f of x to 0. And let's do that right now. So first let's find the derivative of f of x, right? That's going to equal to 3x squared minus 6x. And we know that the critical values or critical numbers only exist at places where the function is equal to, the derivative at that x value does not exist or it equals to 0. We know that this right here is a continuous parabolic function. Therefore, we're not going to have any discontinuities and we can never have a vertical tangent. However, we can have a horizontal tangent and we're going to find that. The way we can test for a horizontal tangent is by setting this derivative equal to 0. So we're going to say that 0 equals to 3x squared minus 6x. And now we're going to solve for the x value. This just requires a bit of factoring. So 0 is equal to 3. I'm going to factor out 3x, and we're going to be left with x minus 2. And now we can clearly see that our first root is when x equals 0, and our second root is when x equals 2. Now we just have to check that both of these x values are within the domain that we're talking about, which is right here, and they both are. So both of these are valid critical values or numbers. So now that we have these x values right here, what we want to do is actually find the value of the function at those values. So f at 0 would equal to 1 because we were just going to plug in 0 to the function and get 1, right? F at 2 is equal to minus 3. And that concludes step number 1, and we're going to move on to step number 2 that tells us to find the values of the endpoints, right? The endpoints are right here. They're minus 1/2 and 4. So what we can do is find the value at them. So now we can see that we have found the values of our critical values right here, and we have found the values of our endpoints. Now all that's left to do is compare to find out which one is the minimum and which one is the maximum. So we can clearly see that f of 4 has the largest y value of 17. So that means that x equals 4 is the x coordinate of our maximum. More specifically, our maximum is going to lie at 0.417. However, our minimum right here, and this by the way happens to be an endpoint, so we can see why it's important to test for endpoints, because if we didn't, then we would have thought that f of 0 was our maximum, but it's not. Now f at 2 we can clearly see has the smallest y value, so the x coordinate of 2 is clearly our minimum, and the minimum value would lie at 2 and minus 3. And now obviously these values give us like extra points that we can plot on a graph, and we could slowly begin drawing out this graph, but we're going to get more in detail about the shapes of graphs and how the derivatives of a function connect with that. As of now, it's just important to understand that if the derivative of a function equals 0, that means that we've hit a maximum or minimum value, whether that be global or local. We won't know until we do a little bit of testing, like you saw here. But and by the way, so we were doing step number 3 here. But yeah, that will require a little bit of testing, as we saw. And then from there we can move onwards and draw our graph. So that's it for this video. It was just kind of a quick video showing how we can use derivatives to find out certain features about a graph. I hope you enjoyed the video. If it's helped you out in any way, like and comment as to what I helped you out with. Like usual, if you are new to this channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will see you guys in another video.